asked to speak at this seminar. So I want to say a few words by way of context. I've been trying to learn something new over the last couple months during my time in quarantine at home, and I wanted to report a little bit about my my experience. And so hopefully you'll bear with me. I have tried to take the things that are new and relate them to things that you may have a lot of experience with before. So hopefully that'll be interesting to you, but this will be light on theorems and more on exploration of some really exciting new ideas. So with that said, let me get started. So let me set some of the guiding questions that motivate this. So throughout, we're going to work with a finite group, G, and we're going to assume that G acts faithfully and birationally on a complex variety. After resolving the indeterminacy and resolving the singularities, we may as well assume that X acts regularly on a smooth projective variety X. So birational actions are sort of where things originate from, but for our purposes, we can do our computations on smooth projective models. And this is a core question that all of you are very well acquainted with. So how do we classify such actions up to birational conjugations, especially in cases where the underlying variety is rational, birational to projective space? And so in this special case, what we're really doing is we're trying to realize a given finite group as a subgroup of the Cremona group, the birational automorphism group of projective space. So this is a very old problem. It goes back to the 19th century. It's such an old and intricate problem that I will not mention anything that happened before my birth, because the 19th century literature is so beautiful and intricate that I don't think I could faithfully summarize it. Many of you know that literature at least as well as I do, so I hope that's not a problem. So this is a question that we want to study. It's a very old question, and I'm going to only mention things that have been done in living memory, my living memory. So the way I see this is the real groundwork for the modern study of these questions was the G minimal model program. So the classification of G birational models, especially of surfaces and how they're connected with each other, how they're linked together. And so Исковskих really did a lot of the key work to put this on a general footing. And so basically the description of minimal models of geometrically rational surfaces and how they're related to each other is very important in understanding the realizations of a group and a Cremona group. So despite this early fundamental work, it took a while for people to give a comprehensive classification, or at least to revisit the work that had been done in the 19th century on these problems. And so this happened relatively recently. Beauville, Bayle, de Fernax, and Blanc, they gave a pretty detailed description of what are the possible actions of cyclic groups and finite abelian groups on surfaces. Further work in this direction was done by Dolgoshev and Исковskих, and they largely completed the surface case, describing the conjugacy classes of embeddings of G in the Cremona group of rank 2. There's been some interesting work by Bogomolov and Prokhorov on the stable conjugacy problem. So you can have G embedded in the Cremona group in dimension n, but when you pass to a higher dimensional Cremona group, they become conjugate even though they were not conjugate in smaller dimensions. And so this is an interesting problem, the stable conjugacy problem, something I'm not going to talk very much about today. But I only mention it because this is one context where some invariants or homological machinery are relevant. And so there are tools that come from Galois cohomology, the Galois cohomology of the group acting on the Néron-Savary lattice of the surface that give you some interesting information on the stable conjugacy question. And for threefolds, there's been a huge amount of work. It would be 4 slides just to list the papers. And so I really can't do it justice. But Prokhorov, Shramov, and collaborators, they have a huge wealth of results on threefolds. There's beautiful results on very specific groups, especially simple groups. And there's also more general structural results, what you can say about the groups that arise in terms of their complexity by various measures. And so there's really a lot of information that has been obtained on these questions. So I think this is a level of summary I'll be able to offer today. So I will say a couple general remarks about the strategy here. So as I mentioned, this work really falls squarely in the minimal model program. And the way I think about this is that the minimal model program, or a G equivariant version of the minimal model program, allows you to choose a distinguished model for whatever birational action that you have, a simplest model, a minimal model, a model that's relatively straightforward. And then you're reduced to analyzing automorphisms for whatever restricted class of objects that come out of that process. So for example, a lot of the work on surfaces boils down to explicit analysis of automorphisms of Del Pezzo surfaces. And that's a huge advance because Del Pezzo surfaces are bounded, they're classified, you can write down equations, write down the automorphisms. And so the birational geometry reduces it to an honest classification problem where you have to write down subgroups of a certain group that have desired properties. So this is sort of at a high level how much of this work proceeds. So the other thing I'd like to mention is that for the most part, the approaches to these things aren't in developing birational invariants, but they really are using these classification machinery. And there's a few exceptions to this that I should mention. Obviously, the work by Bogomolov and Prokhorov using Galois cohomology from the neural-spheric group is an exception. And the classification of Blanc for cyclic actions on surfaces, it uses an invariant called the normalized fixed curve with action. And if you haven't seen this before, I will say a little bit more about it in our examples later on. But basically the idea is that when you have a cyclic group acting on a surface, if you're lucky enough that there's some high genus curve that's fixed by the action, that curve and the action of the group on the normal bundle is an important invariant of the action. And so this has been used to great success to give a relatively conceptual description of the various cases for cyclic group actions. But largely, invariants are not really the traditional tool in this. It's really using these very robust and sophisticated classification techniques. So I'd like to go in a slightly different direction, but I want to describe the invariants and make close reference to some of this other line of work that has been so successful over the last few decades. And so let me move on to introducing the basic invariants that are useful. And so I have almost no responsibility for these invariants. So this is work that was initiated by Kontsevich, Pashtun, and Schinkel. And so I just wanted to give you a presentation of how they approach things. And so you start off with a smooth projective variety. Again, I'm always going to be working over the complex numbers today, although there are things you could do over non-closed fields, but I think the complex numbers is enough. And let's, for simplicity, just look at the case where you have a cyclic group of prime order acting on this. And so when you have a cyclic group of prime order acting, you can look at the fixed point loci. And so I'm going to take this as a disjoint union of smooth closed subvarieties indexed by alpha. So we have the F alpha. So this is the simplest possible case because any point on X that has non-trivial stabilizer is actually a fixed point. And so it just makes it easier to present the basic structures. So so you have these fixed points, and since we're working over the complex numbers, we can diagonalize the action of this cyclic group on the normal bundle, and we keep track of the weights for that action. And so these weights are characters for our cyclic group CP. So that's the weights of the action of CP on the tangent space to a representative point on the fixed point locus. And so we're basically picking some random point on the fixed point locus. We're not keeping track of what it is, and just encoding what is the action of the tangent space. And so these F alphas, I probably should have said they're smooth, closed, connected subvarieties. And so obviously we want these weights to be an invariant on an alpha. And so then what we simply do is we encode these into a symbol. And then the desired invariant, which is not an invariant yet, but at least is something that I can write a formula for. So this is beta for CP acting on X. Is I simply sum over all the fixed point components and keeping track of these weights. And so I'm going to talk in subsequent slides about how to actually get an invariant, but I at least wanted to show you how to compute the quantity to get started.
Can I ask a question? So
please go ahead.
When you say weight, what for you, what is a weight? Are you fixing an identification of CP with the piece roots of unity, and then thinking of the A's as integers, or what do you mean? So
I'm going to come back to this in a moment, but I'm thinking of a homomorphism from CP into GM.
Okay, so each AI is one of those.
Yes, each AI is a homomorphism from the multiplicative group into GM.
Okay.
Are there any other questions? Okay, so let me just write a couple examples. So obviously the easiest examples is diagonal actions on the plane. And so we have zeta as a piece root of unity. And I just wanted to give you an example of what the symbols look like. And here I'm abusing notation using these integers between 0 and p as stand-ins for the characters. Hopefully that won't be too problematic. And so this action on P2, there are 3 fixed points corresponding to the coordinate axes. And in each case, I just dehomogenize, look at the weights, and record them here. So this is the easiest example. Another example is that you could have a cyclic group acting on a degree 2 Dalpetzel surface by the covering map. So the degree 2 Dalpetzel surface is a branched double cover of P2, branched over a quartic plane curve. And the covering involution is just W goes to minus W. And I just keep track of that symbol, which is not much information in this situation. So I do want to emphasize that we do keep track of the symbols even when only some of the eigenvalues are non-zero. We don't need to have isolated fixed points. Okay, so now the next slide will hopefully clarify things for Bjorn if I didn't do a good job in my answer. So let me sketch the overall algebraic structure of the invariants here. So let G now be an abelian group, finite abelian group, of course, and let A be the characters of that. And we are going to let N be the dimension throughout, a positive number. And so we introduce a free abelian group on the symbols I wrote down before. So these are symbols A1 through AN, where I choose the characters in such a way that they generate the group A. And so then I want to construct a group Bn of G. And so it's going to be a quotient of this free abelian group on these symbols, subject to the following relations. So if I simply permute the characters, it doesn't change what the symbol is. And so remember, let me go back a little bit. my motivation was to have this beta be well-defined, to have a well-defined invariant that, that reflected just the structure of the fixed points and the action on the normal bundles. And so here, ordering the eigenvectors on in the normal directions or the tangent directions is arbitrary. And so I need to allow myself to permute them arbitrarily without changing the symbol. And the second relation is a bit more complicated, but the idea is that if you have, say, a fixed point, I can always blow that up. And when I blow it up, I'm going to get an exceptional divisor, and the exceptional divisor will have an action for the stabilizer. And there may be fixed points on that exceptional divisor. And I need to keep track of the bookkeeping of those fixed points. And so this is how I'm trying to do this with this somewhat complicated identity. And so essentially this is saying that if I blow up a stratum of codimension k, where k goes from 2 to n, I need to do some bookkeeping in terms of what are the fixed points upstairs in terms of the weights on the normal bundle downstairs. And so I don't know if I want to say much more about this other than what I've written down, but I just want to say, in an example to try to clarify things, going back to P2 with this diagonal action, I can blow up each of the points that are fixed and keep track of what is the action on the P1. And then on that P1, since I have a group acting, I can keep track of the 2 fixed points and just recording the weights for the action of those 2 fixed points. And so hopefully you can see that it's fairly straightforward when you're blowing up these G invariance stratum, what happens to the fixed points and their weights as you go through the blow up process. Okay. And so Bn of G is just the quotient under these relations, a permutation relation and a blow up relation. And so we can do this, we can define an invariant not just for cyclic groups, but for arbitrary abelian groups. So again, we look at the fixed points for the action of G, and I decompose them as before. And we look at the weights on the tangent space, and we construct this invariant by summing the symbols over the weights. And it's a theorem due to Konchevich, Peshtun, and Schinkel that this gives you a well-defined invariant in this group Bn of G. I want to emphasize one thing here. I am ignoring a lot of information. So I am completely ignoring any of the geometry of the fixed point loci per se. The fixed point loci could be points, they could be 37-dimensional varieties, and I completely ignore all the geometry for the time being. And so in many applications, that's a mistake. And so we'll come back and refine the notion. The other thing is that we're ignoring points that are not fixed, but might have non-trivial stabilizer. So if you have a cyclic group of composite order, you may have something that is fixed by a subgroup, but only stable under the full group, or something that is, that has non-trivial stabilizer, but is not actually fixed. And we're not really keeping track of that directly. And so we'll come back to refinements that encode that information later. But I'm not going to do that at the moment. All right, so let me pause for a moment. Are there any questions? Okay.
Sorry. For example, if
yes.
if your group is simple, then you don't have any characters, right?
Could you say it again? I couldn't hear the first part.
If your group is simple, you don't have any characters at all, right?
Well, I mean, the only simple abelian groups are the groups of.
Your group is abelian. Okay, sorry.
I will come back to non-abelian groups in a moment. But I wanted my general approach is I'm going to start with the simplest constructions and sort of spiral out from there. And so obviously there will be simple groups later in my talk, but let me start with the easiest groups.
Okay. Sorry.
That's fine. I think you're a few slides ahead of me. Are there any other questions? Okay, let me move on. So I'm going to talk a little bit about surfaces. The G equivariant birational geometry of curves is probably pretty well understood. So let's focus on surfaces. And so the first thing I want to do is just to talk about the structure of these invariants, focusing on cyclic groups for the most part, because the structure is pretty intricate. And frankly, it's not that well understood. So I'm going to go back for a moment and just write down so recall that we're just taking this free group generated by the symbols, and there's only a finite number of symbols. So this is a finitely generated free abelian, finitely generated abelian group. It might have torsion. And we're imposing these relations, and well, what do we get when we do that? And so there's some tabulations here. This is again due to Kontsevich, Pashtoon, and Schinkel. So in the one-dimensional case, even though there's not that much interesting birational geometry, we can still compute these invariants, keeping track of the possible fixed points for cyclic groups. We only have to worry about cyclic groups because that's kind of all that you can see on in a one-dimensional representation. And so these are generated by this phi is an Euler phi function. The integer is relatively prime to n mod n. So in the case of surfaces, the groups have both a torsion-free part and potentially torsion. And so I tabulated the first few ranks here. And so this is all in dimension 2 and letting the order of the cyclic group grow larger. And so for primes, there's a pretty nice expression for these groups. So for the cyclic group of order 3, you get something of rank 1. And for cyclic groups of order p greater than 5, or p is a prime, the rank is given by this formula. And so this suggests that there should be a connection with modular symbols, which I'm not going to talk about. But so there are a lot of different ways of computing and organizing symbols that seem to be related in intricate and subtle ways. And so this is a hint that, that these fit into some larger, more conceptual picture. So anyway, we have this formula. So when we have abelian groups that are not cyclic, you can also compute these things. And so it turns out that the Klein 4 group is pretty interesting for examples I'll look at later. So I tabulated that. And you can have torsion. Torsion is pretty common in this machinery. And I just want to point out that you can have torsion. Let me reset them. So when you have a cyclic,
Line 4 seems to have a typo. The dimension is what's supposed to be that saying?
Just eliminate the dimension. So it's only supposed to be B2 is equal to. There's no dimension. Sorry about that. So if you look at the groups for n equals 6, 7, and 8, there's torsion that's not, there's torsion. There's a torsion part to the group killed by 2. So these groups have both a free part and a torsion part. So let me give some concrete examples. So first of all, you might say this invariant is useless because take the most fundamental example of Cremona transformations, which are involutions on surfaces. So if you go back to this tabulation, there's nothing for n equals 2, there's no information that you get from this machinery. And my training as a graduate student is you always take whatever machine that you want and apply it in the most classical and interesting examples. And so these would be things like Bertini and Geisser and de Joncory involutions, and you get nothing in those cases. And so that is maybe a little discouraging, but I want to point out that there are things that you can do to refine these invariants that actually do allow you to get information in these cases. So if you remember in the analysis, I completely ignored the geometry of the fixed point set. I only just picked some random point, looked at the weights, but I completely forgot about the underlying geometry of what's fixed by this element, by the subgroup Cn. And so that's obviously not a good thing to do if you want to classify involutions on surfaces. And so this machinery admits a pretty natural generalization where you add the stable birational equivalence class of the fixed point locus into the invariant. And so then it carries a structure that's more intricate than just a finitely generated abelian group, because you're encoding these stable birational classes. And so when you do this, when you encode these stable birational classes, the relevant contributions of the B groups is in lower dimensions. So what you have in general is that in dimension n, you get contributions involving these BM of G's, where the symbols incorporate the stable birational equivalence classes of the fixed loci that appear in codimension M. So B1 contributes in codimension 1, B2 contributes in codimension 2. And so these refinements are actually quite useful in doing computations in many cases. And so these refinements allow you to get a bit more information than you can get just by looking at the invariance per se. But knowing the invariance is important because if you want to get something, in codimension 1, the algebraic structure of B1 is what's relevant. Something in codimension 2, the algebraic structures of B2 are relevant. And so there's certainly nice interactions between the algebra of invariance and the birational geometry of these fixed point strata. And so I just wanted to point this out, that yes, it says nothing about the classical involutions, but there are ready generalizations that allow you to approach these questions. So let me say something about actions of order 3. So now you do actually have invariance. And so the B2 of C3 is Z. And so I wrote down some of the relations. And as you might hope or expect, the actions of the cyclic group of order 3 on P2 or P1 cross P1, they have trivial invariance. And so that's a good sign, because you want these to be, these are birationally trivial. The things equivalent to linear actions are trivial objects. There are actions that can occur with fixed curves, like the cubic surfaces that are cyclic cubic covers of the plane, or these degree 1 Del Petzl surfaces with order 3 automorphisms. And in these cases, you have an invariant that takes values in a B2 of C3. But if you want to really get a classification statement, you need to also take into account the stable birational type with a fixed point locus. So anyway, let me turn to some of the generalizations that allow you to capture this information. So let's assume that you have a faithful action by G on a smooth projective complex variety X. Now we don't necessarily assume that G is an abelian group, but we do insist that the stabilizers be abelian. So this might seem like an unreasonable thing to do, insisting on abelian stabilizers, but it turns out that there are standard ways to force the stabilizers to be abelian. And so if you look at the locus of an X with non-trivial stabilizer, and basically the intuition is that you kind of blow it up to try to make it look like a normal crossings divisor. So for instance, on a surface, you might have three curves that have non-trivial stabilizer meeting at a point. And so then, oh, you want to blow those things up. So you might imagine that there's an S3 stabilizer where S3 is a symmetric group. And then you have codimension 1 loci that are stabilized by, by transpositions, and you want to blow up the point with the S3 stabilizer. So you can always blow up so as to achieve that all the stabilizers are in fact abelian groups. And so this is essentially some version of embedded resolution of singularities for the stabilizer locus, where you blow it up to get a normal crossings divisor. But the sort of the technically sophisticated way of putting this is that you use a divisorialification algorithm of Berg and Reed and apply this to the quotient stack. So this is a sort of a more highbrow way of saying, blow things up if you have stabilizers that are non-abelian. And so there's a general technical formalism that allows you to do this. All right, so we have that all the stabilizers are abelian groups, which is good because then most of the machinery that we introduced, if you go back to this algebra invariance, it was really designed with abelian stabilizers in mind. But since we made the stabilizers abelian, most of this just goes over without much change. And so then these Kresch-Chinkel invariants, which are refinement or sort of a stronger version of the Kontsevich-Pashtun-Chinkel invariants. So you allow non-trivial stabilizers, and for each of them, you keep track of a number of pieces of data. The first thing that you need to do is you look at the normalizer of that subgroup. That normalizer will act on the stratum or the orbit of the stratum. And so you want to keep track of that. So you might, if you have stabilizer H, then you look at the group G, it pushes things around a bit, and you want to keep track of that action. And you also want to keep track of the action of H on the normal bundle of the relevant stratum. And so you can define invariants similar to the invariants I described before. You have a blow-up relation that allows you to keep track of what happens as you blow up under some varieties that are G invariant or H invariant for subgroups H. And they're more complicated, but they're substantially similar to what was written before. So I'm not going to write them down here, but there are things analogous to this second relation where you just keep track of the bookkeeping of what the stabilizers look like as you blow up various stratum. And so for cyclic groups acting on rational surfaces, this has all been done before. So there is the NFCA invariant of Blanc, where you, if you have a cyclic group acting on a surface, you look at all the cyclic subgroups. And for each cyclic subgroup, you look at all the loci fixed by those cyclic subgroups, and then you encode the data of how the subgroup acts on the normal bundles to these strata. And so this is essentially equivalent invariant to what the Kresch and Chinkel invariance does. It's just encoding all that additional information. Okay. So let me give an example that gives some indication of how this works. Is there a question or?
Yes, I'm wondering how you put them together. You can do this for every abelian subgroup, say up to conjugacy. Is that all it is, or do you somehow take into account how these groups, fit together inside of G?
Well, so you identify groups H and their and the conjugate groups. So I mean the invariant is really on a conjugacy class of abelian subgroup. You also keep track of sort of, I mean, if you have two subgroups that intersect, you have to keep track of, those abelian subgroups. But the only thing that you really do look at is abelian subgroups and how they intersect with each other. So I don't know if that answers your question or not. The fact that we've blown up to make all the stabilizers abelian, in some sense, it's replaced some of the group theoretic complexity with complexity in the geometry of X.
That answers my question. Thank you.
Okay. Are there any other questions? Okay, well, since this is the Исковskih seminar, I think I am duty bound to try to have an example that goes back to Исковskih. And so Искovskih gave an instance where there, in the Cremona group for P2, there are two non-conjugate copies of the cyclic group of order 2 with a symmetric group on 3 letters. And so one is sort of an additive example. So you look at a plane x1 plus x2 plus x3, and you consider the permutation action that just permutes the numbers 1, 2, and 3. And you also allow yourself to reverse the signs. So I've written this in affine form, but you can certainly extend this to get a linear action on P2. So that's one action. And the other is a multiplicative action where you look at a torus, y1, y2, y3 equals 1. And you, again, take the permutation of the letters. Instead of reversing signs, you take inverses of all the letters. And so this gives you an action on the torus, and it compactifies to give you an action on a sextic del Pezzo surface. In fact, it's a well-known fact that a sextic del Pezzo surface, the sort of the part of the automorphisms modulo the connected automorphisms is a product of S3 cross C2. So you're basically just picking those things up. And so the model, the P2 and the sextic del Pezzo surface, from our perspective, they're not good models because you have specific points like the origin that has a large non-abelian stabilizer. And then you have the point 1, 1, 1, or the diagonal cube roots of unity that have non-abelian stabilizers, and we don't allow those, so we blow those up. And so then you kind of keep track of the bookkeeping of the P1s that are stabilized by the central element and have a non-trivial symmetric group action. And that's what you get when you blow up these points with the stabilizers. And you get different, you can just count that they have different numbers of representatives with these actions, different numbers of divisors. And one thing I want to emphasize is that once you've blown up, so that you're in a situation where all the stabilizers are abelian, you can't blow up further and get a stratum that has a stabilizer, a symmetric group on 3 letters. And so basically you can get an invariant of the Kontsevich-Chinkel group where you extract out the number of these P1 components that have an S3 action. And this allows you to differentiate these two S2 cross C2 cross S3 actions on surfaces. So this just gives you, of course, this is a very classic example that is easily addressed using tools of classification theory. but I think it's interesting to see by keeping track of the loci with non-trivial stabilizers and how they're acted on by the normalizer of that stabilizer in a larger group, you can get an invariant that allows you to distinguish these actions. So you just have different numbers of strata that have these two different characteristics. So in other words, I'm going through and I'm taking this analysis of the stabilizers and the normalizer actions, and I'm using this to get some information on these planar actions. Okay. So let me turn to threefolds. I mean, I could go through and do a lot more on surfaces, and so we're still doing lots of computations, especially with non-abelian invariants, to see to what extent they give you allow you to recover the classical results of Dolgotchev, Исковskih, and others. And so that's still an ongoing process, but I just wanted to show you some illustrative examples for threefolds as well.
Sorry, and just a question about the previous slide. So that the conclusion is that these two examples are distinguished by the invariant, right?
Yes. The punchline is that the Kontsevich, the Kresh-Chinkel invariant, where you keep track of the stabilizers and the corresponding strata, they can be used to distinguish these two actions of C2 cross S3. These two subgroups in the Cremona group.
So do you also need the symbol in that example, or is it just the fixed point locus?
Here we actually don't need the symbol. We just need to have a P1 with, I mean, we do keep into account the birational, the stable birational type of the stratum. But once I've done that, I don't need to keep the symbol per se. So I do need to keep track of the fact that you have a P1 with an S3 action.
And what about, so in the two-dimensional case, suppose that you keep track of everything, of the fixed point locus of the symbol, and if the fixed point locus contains some curves of higher genus, then also keep track of the isomorphism class of this curve. If one takes into account all of this, other examples, does this invariant become sharp or what?
Costa, I lost you.
Sorry?
Someone had interference. So can you repeat what you just said?
Yeah. So suppose that you keep track of everything which you explained on the previous slides.
Yes.
Of the fixed point locus, of the invariant, if you have some curves of higher genus in the fixed point locus, then on the isomorphism class of this curve. So does this invariant, say in dimension 2, already distinguish everything?
Yeah, so I don't know that. So the invariant has only been created in the last few weeks. So I don't know whether it is a complete invariant. I think it's it is the natural question to ask. So in this case, they keep track of the stable birational equivalence class of the fixed point loci and the action. So there's you look at the action of the normalizer as well. So that's like the S3 action on the stable. So you're keeping track of the stable birational geometry of these invariant loci in smaller dimensions. So it's not just the curves, it's the curves along with the group actions. But I don't know whether this is enough. I think it's a very reasonable question. And this stuff is new enough that I just don't think it has been completely addressed yet. Yeah, that's kind of why I'm giving this talk. Are there any other questions before I go on? A quick, do I end at 12? I'm sorry, at 1900 or 1930? Is there?
No, whatever you like. We're
okay.
It's like usually between 1 and 2 hours, and some people prefer to speak longer.
I prepared a little bit more than an hour, so
that's very good. Very good.
Okay. Then let me continue with the threefold cases. I can't hope to give a comprehensive example, but I just want to show you some illustrative instances. So first of all, let me show you the structure of the invariants. And so the non-torsion invariants for small cyclic groups, you don't see very much for small n. They do get large eventually as n grows. And there's a lot of interesting torsion structures that you come across for various primes. And so I bolded the primes where you have non-trivial torsion, just as an indication. And so, yeah, so it's interesting. I don't think that we have a really comprehensive description for when there will be torsion and what the order of the torsion will be. I think it tends to happen when the primes divide, I think the order of the group -1, but I don't really know. So this is these bold letters are bold numbers in this table are pretty mysterious to me. But I just want to keep them in mind, because when we look for examples where these invariants can be distinguishing, well, this tabulation is potentially relevant. So let me take an example that is near to my heart to show you both what the invariants can do and how they can fail. So let's look at complete intersections of two quadrics in P5. So smooth complete intersections. They can be simultaneously diagonalized over an algebraically closed field. And a key invariant is the degeneracy locus of the pencil. Just if I think of this as being a pencil of quadrics, I look at the elements of the pencil where the rank drops. There are 6 such elements, reflecting the fact that these are given by symmetric 6x6 matrices. And so this is an invariant, these 6 points, regarded as a subset of P1. And so I can describe the automorphisms of X as being related to the automorphisms of this configuration of points. But there's a bit more that comes from the fact that the 2 elementary group associated with diagonal matrices with ±1 entries, they can act in such a way that you don't really see how it acts on the level of the degeneracy locus in the pencil. And so the automorphism group here is a semi-direct product of these two things. And thankfully, Avalov has undertaken a pretty systematic analysis already of how do these varieties fit into the G-minimal model program. And so this is a good test bed for how these invariants can distinguish various cases. One thing that we also know is that we have a clear criterion for when these complete intersections of quadrics are birationally trivial. And so I should have said that these are G rational if and only if they emit a G invariant line. So they're G rational to projective space if there's a line that is invariant under the G action. So this is a test case that we'll look at. And I want to present one example. So probably the simplest example is when you have a cyclic group of order 2 acting by this matrix. And so this essentially corresponds to a two-torsion translate on the variety of lines. And so as such, when you translate something by two torsion, the one thing you can see for sure is that there's going to be no fixed points. So since this is two torsion translation on the lines of X, these are not rational. But none of the machinery that I presented up to this point, none of it will allow you to see this. No matter how much I throw in the stable birational equivalence classes and such, I don't know how to use the existing simple machinery to get a non-trivial invariant here. So obviously the simple invariants, even when you throw in the additional data for stabilizers and the stable birational equivalence classes of the fixed point loci, so it does not give you something useful here. So it's not so hard to show that even though you have an elliptic curve here in a fixed point locus, even taking that into account, even taking the stable birational equivalence class of the elliptic curve and including into the invariant, you don't get anything non-trivial in this case. So there are limitations to this. It's not a complete invariant of a G birationality. But when you make the group slightly bigger, you get some more. So here I'm going to take, it's shortest for me to write this in a non-diagonalizable form. So let's take this pencil and we allow ourselves to exchange x0 and x1. And then we look at the matrix I wrote earlier on, where I take -1 on the first two and +1 on the remaining ones. And so here you do get a non-trivial birational invariant. And so this is not super surprising because we know already that there are non-trivial elements in B2 for the Klein-4 group. And so there's some space for these invariants to actually work on. So we're taking that into account in this case. So I was asked about simple groups, and simple groups are pretty hard, in fact. So I'm going to show you what our attempts to use this stuff to analyze one of the most beautiful central examples for actions of simple groups. And so by way of motivation, let me point out that one of the first prime where B3 is non-vanishing as a vector space is P equals 11. I'm going to go back to the tabulation. So this is the first prime where you have a non-trivial invariant. And so let's see if we can actually use that invariant to do something interesting. And so my favorite group that has 11 piece is the PGL2F11. And this has a well-known beautiful action on a number of threefolds. None of these threefolds are rational over the ground field, so this is not really a Cremona group problem, but it's close enough. We are looking at actions on Fano varieties, and I think it's in the spirit of this. So I wrote down a specific antisymmetric matrix that has a Pfaffian cubic form with a highly symmetric equation. So if you notice, this is obviously symmetrical through a cyclic permutation of the 5 variables. It's less obviously symmetrical under the action of PGL F211. And so if you really want to get into this, you should observe that PGL F211 admits actually SL2F11 admits a 6-dimensional representation. And if you look at how that acts on the corresponding Grassmannian GER2 6, you can get a natural description of these Pfaffians by just doing invariant theory. I don't have time to present that now, but I'll just say that you get a cubic threefold, a smooth cubic threefold, something that goes back at least to Klein he used this in the study of modular curves with an action of PGL2F11, and this is compatible with a Pfaffian representation as a Pfaffian of a 6x6 antisymmetric matrix. So what can we say about this? Well, let me go in the other direction. Sorry. So there is a dual Fano threefold of genus 8 that comes from the representation theory of SL2F11. And so this is realized as a codimension 5 linear section of the Grassmannian GR26 with these equations. So these are sort of specializations of Plücker relations from the Grassmannian, but on restriction to a codimension 5 linear section. And that gives us another Fano threefold of genus 8. And this also admits a G action, where G is PGLF211. So how are these related, and how can we understand them using our symbols? Well, so X and Y, the cubic threefold and the Fano variety of genus 8, they are birationally equivalent to each other. They are even stably birational equivalent in a way that is compatible with the G action. So there are many ways to see this, but maybe the nicest modern approach is homological projective duality, the construction that relates the cubic threefolds with these codimension 5 linear sections of the Grassmannian. It gives you a lot of tight relationships between the cubic threefolds and these Fano varieties. And it's very, very natural in families. And so it is enough to give you a G equivariant stable birational equivalence between X and Y. So there's a natural P1 bundle over Y to which the G action lifts that has a property that a section of that by hyperplane is birational to X. So these are tightly related even in the G birational category, but they are unfortunately not birationally equivalent to each other for G. So there's work of Shromoff and Cheltsov that shows using the factorization results and analysis of linear series that they're not G birationally equivalent, even though they're G stably birationally equivalent. Unfortunately, we were hoping that we'd be able to see this by looking at the 11 CELO subgroup of PGLF211, by looking at the cyclic groups of order 11. Remember that we have an invariant for cyclic groups of order 11. We were really hoping to use this to distinguish these examples. Unfortunately, that's not the case. So we dutifully computed the fixed points for the equations here and here under the action of order 11. And we saw that the invariants, the Kontsevich, Pestun, Tinkle invariants, they are equal on both sides. And in retrospect, this is quite unsurprising because for any abelian group, the representation theory that gives you the constructions of X's and Y's and their duality, that representation theory gives you a birational equivalence for any group whose irreducible representations are one-dimensional. And so for any abelian group, X and Y are in fact birational for that action. So this is a little bit disappointing, but it also encourages me to look more carefully at the non-abelian extensions and look at the structure of the stabilizers as you go over all subgroups of PGLF211. So I'm just over an hour, so I'm going to come to the last bit. And so this is really just one slide to kind of whet the appetite for future work. So let's look at cubic fourfolds. So let X and P5 be a smooth, complex cubic fourfold. Obviously, the rationality of these is a pretty solid problem. I don't think we have.
About the previous slide.
Yeah, go ahead. Let me.
As you used to say just before. So what's the punchline of this example? So it is an example where the invariant is not sufficient to distinguish the situations, right?
Yeah, the punchline here is that the abelian invariants are insufficient to distinguish these examples.
I see.
So if we just look at abelian groups and look at the Concevers, Pashtun, Chinkel invariant, we cannot distinguish between these.
And what? So your previous approach was to look at the whole group, but blow up sufficiently many times so that the stabilizers are abelian, right?
Yeah, and that may in fact work. So I don't know whether we are still computing whether the Kresh-Chinkel formalism will allow you to distinguish these. And if it were to work, it could work for any, it could work for groups other than the full group PGLF 211. It could work for other subgroups of the group that are non-abelian. So there are other maximal subgroups. So it's a pretty involved computation to evaluate all the stabilizers of this. There's a lot of cases to look at, but there is a chance that the Kresh-Chinkel invariant could actually distinguish these. So, but the abelian invariants do not.
But the non-abelian invariants depend on the birational model. So why would they be relevant here?
Well, there is the non-abelian invariants. So there's a blow-up relation for the non-abelian invariants, and that blow-up relation does give you a G equivariant birational invariant. So when we describe the symbols, so we described, what are the basic generators, and then there were relations that come out of the blow-up process. We blow up an invariant stratum or a stratum that's invariant under some subgroup of the group, and then we compute what happens to the symbols under that operation. And so you do get a birational invariant, but in general, it's hard to compute. But there is an invariant that comes out of it by following the strategy I laid out before. So Novi, does that answer your question? I know I didn't write out all of the relations, so it would take me probably 2 or 3 slides to do that.
What I'm confused about is that
Go ahead.
we know that there is a birational model where all the stabilizers are abelian. So it seems like whatever birational invariant you can write down that involves non-abelian groups, that should eventually, by blowing up, you can prove that it vanishes, that it has to be 0. So that's the part that's confusing me.
Oh, so you're saying that if that this vanishing here would force any other invariants to vanish?
Well, you have some birational model where there are no non-abelian stabilizers. So it seems like anything that you write down that depends on fixed points for non-abelian groups would have to, that component of it would have to be 0.
I think the issue is that as you go over all the different conjugacy classes, there could be a lot of structure, as you go from one abelian group to another, that, how the groups kind of fit together in the larger group G is relevant as well.
Okay, maybe we can discuss this later.
Okay.
I don't want to hold this up.
So the last thing I want to talk about is for cubic fourfolds. Some of this I may have said already. I'm sorry if I'm repeating myself. So we don't have examples, at least I don't know how to prove that any smooth cubic fourfold is irrational, although there are ideas as to how to do this. But if you look at cubic fourfolds with group actions, you can find instances where they are not birationally trivial as G varieties. And so even the original Kontsevich-Pashtun-Schinkel invariants are sufficient to do that. So thankfully, a number of authors have systematically classified cubic fourfolds with very large order automorphisms. And so if we look at some of those explicit examples, like the automorphisms of order 36 and 48, you can cook up instances where the original Kontsevich-Pashtun-Schinkel invariant is non-vanishing. And so that's saying that this cubic fourfold, it cannot admit a birational map to P4, so that the C36 action on the cubic fourfold ports over to a linear action on P4. So, and there's a similar example, slightly more complex, for a group of order 48. So one irritating thing about the first two examples is I am not sure whether the cubic fourfolds as they're written are rational without the group action taken into account. So they have very intricate Hodge structure, and so it looks good, but I have not done the computation to show whether they are rational or even predicted to be rational based on the Kuznetsov philosophy that if you see a K3 surface, it should be rational. So these examples are a little bit frustrating because you could say, well, that maybe they're not rational at all. But there are, in fact, Pfaffian cubic fourfolds that are given by the Pfaffian matrix I showed you before, which are necessarily rational, but have an action of a cyclic group of order 6 with non-vanishing invariant. So there are geometrically rational cubic fourfolds with cyclic group actions, so that the cyclic group actions are not conjugate to the standard diagonalizable actions on projective space. Okay, so I think that is what I have prepared for the moment. So let me cede the floor to questions.
Yeah, let's thank the speaker. So, any questions?
I have a question. In the beginning, to show that your symbols are invariants, what do you need? Do you need resolution of singularities, weak factorization, something like this, right?
You need resolution of singularities and you need weak factorization. Yes, you need all the machinery. I think that I think that trying to do this in positive characteristic would be pretty daunting. I mean, maybe if you're looking at groups, it would probably be easier if the order of the group was prime to the characteristic. But yes, I mean, even, let's see. Yeah, so I think we do need the weak factorization, because in some sense we're taking the maps and we want to say that we can sort of break them up into blow-ups and blow-downs of specific kinds, where you can actually execute this computation. Yeah, so, but isn't that, I haven't thought hard about whether you can get around it for groups with order prime to the characteristic. So maybe, maybe you could do something.
I see.
In small dimensions.
Maybe the same question about compact complex manifolds. If you look at the same thing, it's also the same question arises, right?
The classification of the actions. Yeah, that's, yeah, I don't know. I should know whether there is existing literature in homotopy theory or differential geometry. I don't know that literature as well as I should. So that's a good question. The extent to which, I mean, there are fixed point formalisms and fixed point localization formalisms in topology that should be related to this. Yeah, that's something that probably should be clarified.
I see. And another question, how about stably rationality, J rationality, stably J birational equivalence? Is it possible to apply this thing to study?
I don't, yeah, so I think that you probably could say, well, if you have a G variety and you have a projective bundle for which a G action lifts, I think you probably could say something about the combinatorics of the fixed point actions. So I think that you probably could get something. I don't know whether it's a useful invariant. But yeah, that seems, if you can find a good model of the projective bundle, where everything lifts nicely, you should be able to compare the structure of the fixed points upstairs and downstairs. And yeah, I don't think anyone has done that yet. I think that's an excellent.
But why not just, I think the most traditional way to understand stable rationality is to start with multiplying your variety by a projective space, right? So, and then the structure of the fixed point locus is very, so to say, straightforward to compare.
Yes.
Just for every fixed point, you have a fixed stratum upstairs.
Yeah, so I think that I was thinking more about how you'd actually prove that you have an invariant, but it's quite possible that what you're saying and what I had in mind would give you the same answer, provided you didn't take, I mean, provided you only take into account the combinatorics of the actions of the groups on the tangent bundle. Yeah, that seems, and what you're doing is eminently computable.
Other questions?
Can I ask, can you go back to the threefold where you had the what was it? The GL2 or PSL2 FL11 one?
Yep.
Where was it? You had some cubic. Yeah, okay. This just reminded me, maybe you know this already. I think Klein proved, you know this fact that Klein proved that if you take this cubic form and you take the Hessian of it,
Mm-hmm.
then the singular locus of that Hessian is the modular curve x of 11. Anyway,
Yes. Yeah. So this cubic threefold is a moduli space of a billion surfaces with certain level 11 structure. And so I think that what you're describing is sort of a natural way to get the modular curve sitting inside that moduli space.
Okay.
So there's a long paper there's a number of papers by Adler, published independently and with Ramanan, where they give very detailed descriptions of the geometry from the standpoint of the modular forms. Sort of like a modern gloss on what Klein did. Yeah, so it's a very nice example. And so it might be the case that the modular interpretation would make it easier to compute, to organize the combinatorics of all the actions. I think that's an excellent point. Right now, we just do it, by throwing everything into Sage or Magma and just computing the eigenvalues of all the matrices. But it is a moduli space. Maybe we should use that to organize what the data should look like.
Okay.
More questions? Well, I have one more small question about the fourfold case. So you say that you know an example of a Pfaffian cubic with a group of order 6 acting on it. And what's the fixed point locus in this case? Is it just isolated points?
I don't think it's isolated points. I think that the fixed point loci actually involve surfaces. So I try to pull up the Magma code, but I think it involves a surface. So
no, I'm not speaking about PGL211 case. I'm asking about the cyclic group of order 6 on the fourfold.
Yes. And I think that was what I had in mind as well. So I don't think that the C6 action here, I don't think it only has isolated fixed points as its fixed. I don't think the fixed points are only isolated.
I see.
I think it's more complicated.
Okay, if there are no other questions, let's thank Brandon once again.
Okay, thank you all.
Thank you. It was very intriguing talk.
It's kind of you to say. Thanks.
Some new machinery on a very old field.
Okay.
Okay. Thank you.
Okay.